Hello students, Sacred Heart High School welcomes you. Today we are going to see in Science-1 Chapter 1 Gravitation Part 2. In this part we are going to see Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it. Now you can clearly see in the picture a girl standing on the road, a car on the road, and a dog jumping. So Earth is exerting gravitational force on these objects. According to Newton's second law of motion, a force acting on a body results in its acceleration. So you can see that the boy exerting force to pull the object. As we know that force is the product of mass and acceleration. So force acting on a body results in its acceleration. As you can see in the picture, a man, footballer, kicking the ball with a force, so it results in acceleration. Thus, the gravitational force due to the earth on a body results in its acceleration. This is called acceleration due to gravity and is denoted by small letter g. Acceleration is a vector. As the gravitational force on any object due to the earth is directed towards the center of the earth, the direction of the acceleration due to gravity is also directed towards the center of the earth, that is vertically downward. Now as you can see in the third picture, a man from the terrace throwing an object. Now you must have observed that when at the initial stage the speed is less, as it comes closer to the ground the speed increases. That's because of the acceleration due to gravity that is directed towards the center of the earth. Now we shall calculate value of g, that is acceleration due to gravity on the surface of the earth. We can calculate the value of g by using Newton's universal law of gravitation for an object of mass m which is situated at a distance denoted by small letter r from the center of the earth. The law of gravitation gives F equal to g m upon r square, as you can see on the screen, where m is the mass of the earth. Now we know that force is the product of mass and acceleration. Now since here we are considering acceleration due to gravity, so we denote it by g. So force is the product of mass and, that is m and g. Now we know that F is equal to mj, so we substitute this value in the equation F equal to gmm upon r square. As a result, we cancel m on both the side and the value which we get is g equal to gm upon r square. Now this value we are going to write on the left hand side, that is g equal to gm upon r square. Now the small letter r can be replaced by capital R because the object is situated on the surface of the earth, as we have said earlier. So the radius of the earth. So hence we can replace small letter r by capital letter R. So what do we get? Now we substitute the value of g, m and r in the equation. Now we know that value of g is 6.67 multiplied by 10 raised to minus 11. M value is 6 multiplied by 10 raised to 24 upon value of r, that is radius of the earth, is 6.4 multiplied by 10 raised to 6 the whole square. After calculating, we get the value as 9.77 meter per second square. So that is the value of G on the surface of the earth, and this is how we calculate the value of G. Now remember that this is the value of G on the surface of the earth. Next we shall see about the variations in value of G. Now first we will consider change along the surface of the earth. Now we have calculated the value of G, but will this value of G be same everywhere on the surface of the earth? The answer would be no. Why? The reason is that the shape of the earth is not exactly spherical, and so the distance of a point on the surface of the earth from its center differs from place to place. Now you can see that due to its rotation, the earth bulges at the equator and is flatter at the poles. Hence, what due to this? Its radius is largest at the equator and smallest at the poles. Therefore, the value of G is highest at the pole, that is G equal to, you can see the value as 9.832 meter per second square, 9.832 meter per second square, that is the value of G at poles. And if you see the value of G at equator, it is 9.78 meter per second square. So we can say that the value of G slowly decreases with decreasing latitude. So it is lowest at the equator. Next we shall see about change with the height. As we go above the earth's surface, the value of r in the equation, as we have already seen, as a value of equation, r increases, that is the radius or the distance increases, and the value of G decreases. That means as we go above the earth's surface, the distance between the earth and that point increases and the acceleration due to gravity decreases. That means the value of G decreases. The decrease is rather small for heights which are small in comparison to the Earth's radius. Let's consider an example. We know that the radius of the Earth is 6,400 km. If an aeroplane is flying at a height 10 km above the surface of the Earth, its distance from the Earth's surface changes from 6,400 km to 6,410 km, and the change in the value of G due to it is negligible. Now we shall see more in detail with few more examples, taking few more examples. Now at the surface of the Earth, as we have seen, the value of G is 9.83 meter per second square. Now if we consider Mount Everest, which is at a height of 8.8 kilometer, the value of G is 9.8 meter per second square. Now as we have already discussed, the radius of Earth is 6,400 kilometer. So if the height from surface to the Mount Everest will be how much? 6,408.8 kilometer, wherein the value of G is negligible. Now let's take another example. Man-made balloon which reaches at a height of 36.6 km. When the value of G is calculated, the value of G is found to be 9.77 meter per second square. So hence here also the value of G, you can see it's negligible, the difference. Now if we consider a height of a typical weather satellite at a height of about 400 km, when we calculate the value of G, it's found to be 8.7 meter per second square. So now you can see the change in the value of G from the surface of the earth to the height of 400 km. Now let's consider the height of communication satellite, which is at a height of 35,700. Now when the value of G is calculated, it is found to be 0.225 meter per second square. So we can conclude that when we consider an artificial satellite orbiting the earth, we have to take into account the change in the value of G due to the large change in the distance of the satellite from the center of the earth. So we can conclude that as the height increases, the value of G decreases. Now let's see the third case, that is change with depth. Now third factor we shall see change with depth. If we go inside the earth, the direction of gravitational force does not change, but the value of acceleration due to gravity changes. While going inside the earth, the value of distance from the surface of the earth, that is r, changes. Now you can see the girl, she goes inside the earth. So as per the formula, if you see the formula, then one would think that the value of G should increase as per the formula because it is inversely proportional to R. However, the part of the earth which contributes towards the gravitational force felt by any object also decreases, which means that the value of capital M also decreases. So if M decreases, the value of acceleration due to gravity decreases. So with the combined result of change in R and M, the value of G decreases as we go deep inside the earth. So as we move deep inside the earth, the value of acceleration due to gravity decreases, and at the center of the earth, the value of G is equal to 0. Now, every planet and satellite has different mass and radius. Now let's see Earth, whose mass is equal to 6.6 multiplied by 10 raised to 24 kg. Radius is equal to 6.4 multiplied by 10 raised to 6 meter. Considering Moon, its mass is equal to 7.4 multiplied by 10 raised to 22 kg. Radius is equal to 1.74 multiplied by 10 raised to 6 meter. Hence, according to equation, that's G equal to Gm upon R square, the values of G on their surfaces are different as we have discussed. So you see this picture. What do you observe? We observe that on the Moon, the value of acceleration due to gravity is about 1/6 of the value on the Earth. So in the second picture you can see that if the same amount of force is used, we can jump 6 times higher on the Moon as compared to that on the Earth. So children, we have understood what's Earth's gravitational acceleration. We have derived the value of G on the surface of the Earth, variation in value of G along the surface of the earth change with height and change with depth.